Hey, IGCSE physics students, are you preparing for your IGCSE physics paper 6? Now you are in the right place because in this video, I am going to discuss Cambridge IGCSE physics paper 6 alternative to practical February-March 2025 paper 62. Are you ready? Let us get started. Let us look at the first question. A student investigates the behavior of a spring and then uses the spring to determine the mass of an object. Apparatus is shown in Fig 1.1. A, the student suspends the mass m equals to 100 grams from the spring. She measures and records in Table 1.1 the stretched length L of the spring as indicated in Fig 1.1. Describe two techniques for measuring the length of the spring to ensure an accurate reading. You may draw a diagram. Since they say you may draw a diagram, I need to draw a diagram. Right, so I have a ruler because I need to measure the length. The apparatus that I use to measure the length of the spring is ruler. And ruler cannot stand by itself, so I need a clamp, retort stand, to clamp the ruler at fixed position. And I just want to make sure that my readings are accurate. So that is why I need to make sure that the ruler is vertical. So that is why I am using set square 1. And then, since there is a distance between the middle rule and the spring, I need a guide. I cannot depend on the air. I cannot just guess the reading on the middle rule. That is why I'm using set square 2 as a guide to the readings on the middle rule. Now, the technique that, I am going to write here is that clamp, middle rule, beside spring, and then you use, set square 1, set square 1 is used to make sure the middle rule is vertical. Set square 2 is used to make sure, not to make sure as a guide. So sorry, it's used as a guide. To read middle rule. And if you want to discuss more technique, right, you yourself, experimenter, you need to make sure that your eye level is perpendicular to the scale on the middle rule. Right, make sure eye level is perpendicular to the scale on middle rule. That's it. Now, the next question, she repeats step A for values of M, which is equal to 200 grams, M equals to 300 grams, and M equals to 400 grams, and M equals to 500 grams. Her readings are shown in table 1.1. Plot a graph L/cm, that's the unit of length. On the y-axis, you have to be clear, L must be on the y-axis against M/gram, that's the unit of mass. On the x-axis. Start the axis from the origin, 0, 0. No choice, you have to start from origin. Draw best fit line, best fit straight line. The line might not go through the origin. So mass, I don't think you face any problem because the gap, right, in each reading is supposed to be 100. So I just put 100, 200, 300, 400, and 500. And L, because I want like easy value, so that is why the gap between the readings will be 5 cm each, right? 10 boxes, 10 small boxes, that is 5 cm gap, right? So I plot all my points here. You see, not all the points are aligned on my straight line, but I just want to make sure that I draw the best fit line. So if you face any problem in drawing the best fit line, here is the tip. What you need to do is find the average coordinate, right, for these values right here. How to find the average coordinate? First of all, mass. right? This is x-axis. You add up all the values on the x-axis. 100 plus 200 plus 300 plus 400 plus 500 divided by the number of readings, which is 1, 2, 3, 4, 5. So divided by 5, you are supposed to get 300. And y-axis, add up all the values on the y-axis. 6 plus 9.2 plus 13.6 plus 16.8 plus 21 divided by the number of readings, which is 5, right? You get 13.3. So this is a point, a coordinate, which we call it as average coordinate, or we call it as centroid. Centroid is a point where a straight line graph must pass through. The best fit line must pass through. That is centroid. So you can label your centroid, but don't put it as X. Just put a dot here. So you look at the green dot that I put here. This is my centroid. So my straight line passes through the centroid. Right. Now, use your graph to determine L naught of the spring with no load on it. When the mass is equal to 0, read on your y-axis because you start from origin. So you can take the reading on your y-axis. My y-axis is 2 cm. So 2 cm is my answer. This is 2. Next one, part D. An object X is suspended from the spring. On Fig 1.2, measure the stretch length Lx of the spring. Right, what you need to do is just to take out your ruler, right? Make sure that ruler is as straight as possible. Just measure from the starting of the arrow, the pointy part, the tip of the arrow, to the tip of the opposite arrow, right? So the length that I measure is exactly 10 cm. So I just put 10 cm. But before that, you just remember you are using cm rule. What is the sensitivity of the cm rule? Sensitivity means the smaller scale on the cm rule, which is 0.1 cm. So since you have already determined your sensitivity of the cm rule that you are using to measure length of x, so the readings that you record must follow the decimal point of the sensitivity of your cm rule, which is 1 decimal point. So 10.0 is the answer, 10.0 cm. Now, the second one, use the graph and your readings from D part 1 to determine the mass mx of object X. Show clearly on the graph how you obtain your answer. So when the length is equal to 10 cm, so you got to look at the graph to determine your mass. So back to the graph, when the length is equal to 10 cm, just look at 10 cm. This is the length, right? Show on the graph what is the value. So the value that I got here is here exactly. This is 200, 210, 220 grams. So the mass will be mx is 220 grams. That's it. The next one, E. The students measure the mass of another object using the same method and apparatus. One student records the mass as 132.6 gram. The other student records the mass as 130 gram. State and explain which answer has the more suitable number of significant figures for this experiment. So I would say that look at the scale. Look at the scale on my graph. Each and every scale, yeah, the smallest scale is 10 gram. So the best, right, to record is 130 gram. Why? Because the smaller scale on graph is 10 gram. Our graph is not as sensitive as 0.6 gram, right? We only have 10 grams. So the best answer should be 130 grams. That's it. Now, second question, a student investigates the effect of insulation on the cooling of water. He uses the apparatus as shown in Fig 2.1. Beaker A is covered with material that is a thermal insulator. Beaker B is identical to Beaker A but has no insulation. Now, A, part 1, record room temperature theta R. Right, shown on the thermometer. So you have to read here. You look at the scale, gap is 10 degrees Celsius. So one scale here, one gap here is 21. 21 degrees Celsius is the answer. Second part, describe one technique used to ensure that the room temperature reading is as accurate as possible. How do we ensure that? So I say that, okay, we clamp the thermometer, right? Wait, okay, wait till the liquid in glass inside the thermometer stops rising before taking the reading on thermometer. Or you can also say that make sure the eye level is perpendicular to the scale on the thermometer to avoid parallax error. Not a problem. So I just want to put something that is different. Now B, the student pours 200 cm cube of hot water into beaker A and records the temperature theta at time t equals to 0. He records in table 2.1 the temperature of the water in the beaker every 30 seconds. Student repeats the procedure for beaker B. It is important that the temperature are recorded as exactly every 30 seconds. Describe a technique which will make it easier for the student to do that. Easier, you just put the thermometer there, just leave it there, or else you have to take out and put it in. Then, right, you might not be measuring the time, the temperature exactly at 30 seconds. So I'll just say that make sure just leave the thermometer inside the beaker. Okay, leave thermometer in the liquid all the time during experiment and okay, students take the reading at every 30-second interval. So you don't have to do a lot of work. You just leave it there every 30 seconds. You time yourself. Okay, you time using a stopwatch and take the reading at 30 seconds, close to 30 seconds, then look at the readings. Yeah. So C, write a conclusion stating whether the insulation affects the rate of cooling of the water. Justify your answer by referring to values from the result. Now, I just want to tell you that part C, there's no correct answer, there's no wrong answer. It is just to see how you justify your answer. Right, so I will count the drop in the temperature in beaker A when there's an insulation from 0 second to 180 second. So the total drop, you take 92.5 minus 85.5, I get 7 degrees Celsius. Whereas for beaker B at 0 second, this is 93 degrees Celsius. At 180 second, this is 83 degrees Celsius. You just minus these two, you get 10 degrees Celsius. Right, so I would say that the total drop in temperature of beaker A at t equal to 0 second to t equal to 180 second is 7 degrees Celsius. And then the total drop in temperature of beaker B at t equal to 0 second to t equals to 180 second is 10 degrees Celsius. Right. So since the experiment, I would say that because it is short period of time, it's about 3 minutes, 3 minutes, 180 seconds is 3 minutes. Since experiment is conducted at short period of time, the difference between total drop in temperature of both beakers is 3 degrees Celsius, right? Which is quite significant or quite large. So that is why I say hence insulation affects the rate of cooling of water. Now, you might say that it is not affecting, but you need to justify your answer carefully and properly. So that is the main thing. That is very important. So you have to bear that in mind. And the next one, D, part 1. Calculate the average cooling rate, X1, during the first half of the experiment for the water in beaker B. Use the readings for beaker B from table 2.1 and the equation X1 is equal to theta 0 minus theta 90 over T, where T is 90 seconds, and theta 0 and theta 90 are temperatures of the water in beaker B at times T equal to 0 and T equal to 90 seconds. Include the unit. So you have to be careful. This is from beaker B. So I'll just put X1 is equal to theta 0 is 93 degrees Celsius minus 87 degrees Celsius when it is at 90 degrees Celsius. And this is 90 seconds. So get a value, I put 0.067 degrees Celsius per second because theta is measured in degrees Celsius and the time is measured in seconds. So I get 0.067 degrees Celsius per second. Second part, calculate the average cooling rate X2 during the second half of the experiment for the water in beaker B. Use the readings for beaker B from table 2.1 and the equation X2 is equal to theta 90 minus theta 180 divided by T, where T is 90 seconds and theta 90 and theta 180 are the temperatures of the water in beaker B at T equal to 90 seconds and T equal to 180 seconds. And you should include the unit as well. So X2 is equal to theta 90, 87 degrees Celsius minus theta 180, which is 83 degrees Celsius divided by 90 seconds. So I got 0.044 degrees Celsius per second. So 0.044 degrees Celsius per second. Do you know why I put it in terms of two significant figures? Because my raw data, theta 90 has two significant figures, theta 180 has two significant figures. Right? So that is why I put it in terms of two significant figures. And x1, same goes to x1. Now, E, a student suggests that for this type of experiment, the temperature of the water in each beaker at time t equal to 0 must be the same for the comparison to be fair. Use the answer. You have to check on your answer from D part 1 and D part 2 to explain whether this is necessary. Okay, now let me find the difference, between x1 and x2 is equal to 0.067 minus, I have to put in the units, degrees Celsius per second minus 0.044 degrees Celsius per second. Let me get a value first. 0.067 minus 0.044. I got 0.023. And I say the difference is quite small. Yeah, the difference is quite small, which is still within, they put here, within the limit of experimental accuracy. Hence, it is not necessarily necessary to start at the same temperature. That's it. F. A student wants to eliminate from the comparison any thermal energy lost from the surface of the water, suggest a change to the equipment which will do that. So you see that these two beakers are exposed to the surroundings. Right? When the beakers are exposed to the surrounding, of course, a lot of heat will be lost to the surrounding from the surface of the water. So that is why cover beaker with lid. That's all. And the second part suggests what effect this change will have on the cooling rates of the water in beaker A and beaker B. So what happened? Lid reduces the heat loss to surroundings from surface of water. Right? So it would take a longer time to cool down the water. So the cooling rate will decrease. Cooling rates of water in both beakers decreases. That's all. Number 3, a student investigates the refraction of light by transparent block. The student's ray trace sheet is shown full size in Fig 3.1. The student places a transparent block ABCD near the center of the ray trace sheet as indicated in Fig 3.1. Draw a normal to point N extending above AB. Label the upper end of normal with letter L. So draw normal, take out my ruler. So I'm supposed to draw drawing. So I want to draw normal, 90 degrees from N, yeah? So I just draw here. And they asked me to label L. So I have to label this as L right here. And we are done with that. And after that, the student draws line EN as shown in Fig 3.1. On Fig 3.1, measures the acute angle theta between lines LN and EN. Where is LN? This is LN, this is EN. So you have to measure this theta. Right, so I put a protractor. You look at my ruler, it's with protractor. So from 90, I shift to this. Okay, look at my protractor. You have to bring protractor into your examination hall. So this is 90, 50. 90 is LN minus EN, which is 50. That will give you 40 degrees. So the answer is 40 degrees. Right, 40 degrees. Right. Now, B, the student, sorry, check it back to 90 degrees, or I keep my ruler first. The student places two pins, P1 and P2, on line EN, as shown in Fig 3.1. First part, measure the distance D between pins P1 and P2. So what are you supposed to do is that you are supposed to take out your ruler, place exactly on P1 and P2. Let me see. So take out my ruler again. Where is my P1? Where is my P2? Oh, there it is. So place your ruler on exact spot, okay? Exact line of P1 and P2. And you measure the length, right? The length that I measured is actually 4 cm. Remember, we are using the meter rule, cm rule to measure, right? What is the sensitivity of the cm rule? Right, it is 0.1. Smaller scale is 0.1. So your D value must be in terms of 1 decimal point, so 4.0. And theta, let me explain. Theta, you are using protractor. What is the smaller scale on the protractor? It is 1 degrees, no decimal point. So when you jot down the value of theta, remember, do not put in any decimal points. Right. The second part, state whether the two pins are suitable distance apart for accurate ray tracing. Explain your answer. I would say no, it's not suitable distance because due to the thicknesses of the pin, right, minimum distance of the pin must be 5 cm and above, right? So I say due to thickness of the base of pin, the minimum suitable distance between two pins must be at least 5 cm. To why? To minimize percentage error of distance measurement. See, the student views the image of P1 and P2 through the block. He places two pins, P3 and P4, so that pins P3 and P4 and the images of P1 and P2 all appear exactly one behind the other. Draw a line through P3 and P4. Extend this line to meet CD. Where is P3, P4? Extend the line to meet CD. Okay, P3 and P4 is here, so I draw. Make sure that you draw nicely. Okay, somewhere here. Meet CD, so I draw, and that's it. What else needed by the question? And with the letter, okay, label the point at which line meets CD with a letter F. Label the lower end G. So this is F, this is G. Right. And then after that, extend line EN to approximately 5 cm. Below line CD, label the point at which the line crosses CD with the letter H. Label the lower end of this line as letter J. So you measure from CD, right, at least 5 cm. Yeah, approximately 5 cm. So you see where is my line of P1, P2. Okay, make sure that, okay, somewhere here. Okay, so extend it 5 cm, yeah? Okay. Approximately 5 cm from CD. So from CD, you measure 5 cm. So from this is CD, approximately 5 cm here, right? So label this as H and this one as J. Done. And then after that, measure D part 1. Measure the acute angle alpha between CD and GH. Where is CD? Where is GH? GH, oh no, CD and GF, sorry, CD and GF. F is here, CD is here. So that is why the angle, I use different colors so that you can see it. So place your protractor between these 2 points, 90 degrees. Okay, this is the angle that you have to measure. This is called, okay, put the ruler aside. This is called alpha. Measure this angle. Right, the angle that I measured was, okay, this is 90 degrees. And then, okay, make sure that, okay, this is 53. So 90 minus 53, I got 37 degrees, right? So 37 degrees, that's my answer for alpha, 37 degrees. And then for my beta, so beta, okay, beta is between, let me read, measure the acute angle beta between line CD and JH. Okay, CD is here, JH is there. So use my ruler again. 90 degrees. Here. Just want to make sure that. Okay. And then move my ruler. I get 50. So 90 minus 50, that gives me 40 degrees. Beta is 40 degrees. Now, the second part, a student suggests that angle alpha should be equal to angle beta. State whether your result supports this suggestion. Justify your answer by reference to the values from your result. I say no. Why? Because the difference between alpha and beta is 3 degrees, which I think is exceeding. So if you want to say yes, it is totally up to you, right? I say the difference between alpha and beta is 40 degrees minus 37 degrees, which is equal to 3 degrees. But if you think that this is small, right, you can say that, okay, which is, if you want to say small, yes, you can say small, which is small. So if you want to say small, okay, the difference is still within the limit of experimental accuracy. That's it. Now, describe two techniques to use in this type of experiment to ensure that your results are accurate. So what are the two techniques? First one, when this is about refraction of light, just say conduct experiment in a dark room. Second, you might want to say, okay, make sure the base of pins are sharp, right? And maybe you want to say that maybe place a white piece of paper so that you can see clearer. Clearer is also okay, right? F, suggest one reason why different students all doing the experiment carefully may not obtain identical result. Carefully, you cannot talk about parallax error because the students have already conducted the experiment carefully. So parallax error can be put aside. So you said that due to the pencil that you use, right? Thick lines, okay? Different thickness of the lines draw. Different thickness of lines drawn by, okay, different students. Some students, they are using blunt pencil. Some students, they are using sharp pencil, depending on how you press it, right? So due to that, we have different answers, right? Now, the last question. A student investigates the resistance of a wire. Plan an experiment which enables him to investigate how the length of the wire affects the resistance of the wire. Resistance R is calculated from the equation R is equal to V over I, where V is the potential difference, PD, across the wire, and I is the current in the wire. The apparatus available includes a selection of the wires, a variable power supply, an ammeter, a voltmeter. In your plan, list any additional apparatus needed. So I need to do this first. You see that, okay, we are supposed to measure the length of a wire, but the ruler is not being given. So what do you think? Voltmeter is being given, ammeter is being given, right? Not a problem. So we can find the resistance. But how to measure length when the meter rule is not being given? Don't you think so? So I would say additional apparatus. I'm going to write it here. Additional apparatus would be my meter rule. That's all. Now, the second part, complete Fig 4.1 to show voltmeter connected to measure the potential difference across the wire. Right, so complete voltmeter measure across the wire. So I don't have to draw a diagram because they have already drew the diagram. So this is my voltmeter. Okay, label this as a voltmeter. That's it. And the third, explain briefly. This is your method, including the measurements to take so that the resistance can be determined. So my method, so I'm going to write it here. Set up apparatus as shown in diagram. Now this is about length of wire is measured. Just give us the apparatus by meter rule. And third, okay, wire is connected to the circuit. Once you measure, is connected to circuit. And number 4, you might want to say that the power supply is given what? Power supply, because this is wire, be sure that the power supply, you have to set it to a small voltage, yeah? Is set to 1 volt, right? And switch on. And what happened next is that, okay, number 5, you might want to say, okay, after you switch it on, readings on voltmeter, which is V, and meter, which is I, are taken. And then number 6, resistance R can be calculated by V over I. Done. And last part of the method, always repeat the experiment. Okay, repeat the experiment with different lengths of wires. Done. And the next one, state the key variables to keep constant. This is a control variable. So I'm going to write here control variables, more than one, because this is plural. I want to make sure that same type of material of the wire. If I use copper wire, all the wires must be copper wire. And maybe temperature of the wire. Wires, and maybe the diameter of the wire. You see that? So as long as you write more than 2, right, you are safe. And then you have to draw a table or tables with column headings to show how to display the readings. You're not required to enter any readings in your table, right? So this is my table. Maybe I use different color, right? Table, this is how I tabulate the table. So I have a length, which is in cm, right? Maybe I just put it here, okay? If you want to use a symbol in your table, you have to explain. So put a comma, L, okay? Put a symbol there, right? So that you can use it in your table tabulation. And then V, voltmeter reading, slash the unit, I slash the unit ampere, and R slash the unit ohm. So this is your table. Make sure that you draw a line, nicer line, right? Not free, right? Freehand like me, right? So done with the table, and explain how you use your readings to reach a conclusion. So in this case, we can actually plot a graph, right? So plot a graph, a graph of L, okay? Length of wire, L, okay, length of wire, which is L, against resistance of wire, which is R, to see the relationship, right? Okay, to see the relation, okay, to see the relation relationship, right? Now, to see the relationship between the two physical quantities, right? If you need the answer in the PDF form, all you need to do is just to comment below. I will send you my answer, right? Thank you very much for watching, and I wish you all the best in your exam, right? So see you again in my next video. Bye.